Hi everyone. Right, first thing to tell you is that today we are going to be doing some hardcore integration, basically all of integration. And I have made you this, let's see if this works. That is a PDF. It's in the exambulance, and I didn't know where to put it because there isn't an exambulance sort of integration type place or like today's lesson. So I put it for future reference in the overview. So where it says exambulance overview, right at the bottom, there's that PDF. Okay. But you don't have to print it. It's got all of the integrals on that I'm going to do today. And it's pretty clever, even if I do say so myself. So what I've done, well, let's talk about where we're at and then what we're doing today. So, no, that's not what I wanted to share. So do I want a different share? I want my iPad. There we go. Good work. Okay, so what have we talked about so far? We started off the week by looking at all of the A-level pure and talking about which bits of that you maybe hadn't done yet, okay? First thing we needed to do was to sort of shore up the integration. So we've done that this week already. So integration is now totally done. And I hope I emphasized to you how important the chain rule is, that the chain rule is really the key to success with not just differentiation, but integration as well. And the chain rule is all of these three here: differentiating, inverse functions, implicit differentiation, parametric differentiation, connected rates of change. If you understand the chain rule, then all of those are just really, really simple. Now, what is vital is that you understand this connection between all of these important topics. If you look at it, are we doing mechanics or stats sometime later on? Look in the exambulance and look at the schedule, and you'll see exactly what is scheduled for when. So go into the exambulance and look on the schedule page, and it tells you what's going on. I will change that if people ask me to, but like at the moment, that's the plan. So integration seems really difficult, but integration is basically trigonometry plus algebra plus differentiation equals integration. So if you can do trigonometry, algebra, and differentiation, then you can do integration, and vice versa. If your algebra is wobbly, your trig is wobbly, or your differentiation is wobbly, then you won't be able to do integration. And it's not even really like there's any more to the integration. It is basically just differentiation, trig, and algebra. Okay, so let's have a look at it. There are basically only 10 things that you integrate, and that's what I'm going to start looking at, the 10 things that you integrate. There are 10 things, and yeah, there's some like level 1 or level 2, but everything is those 10. So everything else that we do in integration, all we're doing is taking something that isn't one of the 10 yet and using trig or algebra to turn it into one of the 10. We only ever integrate the same 10 things, I promise. So what are the things that we can change? We've got fractions. We might need to fiddle around with some fractions. We might have trig that we need to fiddle around with until we get it into one of the 10. We might have some trig functions squared, or there's other trig things like, for example, sine cubed x cos squared x, stuff like that, or sine 5x cos 3x, stuff like that. And there's also parts, integration by parts, and then integration by substitution. So we need to learn, first of all, the 10. What is the point in learning integration by parts if you can't integrate the thing you create by doing integration by parts? What's the point in doing substitution if you can't then integrate the thing that you get by doing substitution? What's the point in me showing you all the fractions and trig stuff if you then can't recognize that the thing you've got is one of the things that you can integrate? So the 10 are the most important, and everything else just gets us back to those 10. The only ones that I'm not going to do today are these, and also partial fractions, because they take quite a lot of work, you know, doing a load of partial fractions and then integrating, or doing a load of trig and then integrating. So I'll come back to those ones another time, but just so that you know that they are in there, and that's the structure of what we're going to do today. The playlist for the next 24 hours is 29, 30, 31, 32. Okay, I'm not going to be doing differential equations today. So it's 29, 30, 31, 32. There's say 10, 15 minutes each. So it's about an hour if you want to make the notes and watch those videos. Let's go. I'm going to put a timer on. There are 35 integrals here, and I've put them all on that spreadsheet, which I'll send you again down here in case any of you, not spreadsheet, in case any of you want to print it, so you don't have to write them down. And these 35 integrals cover everything, okay? They cover everything. Timer and target. The timer is going on for 45 minutes. That's an action hour. And the rules of the action hour are that we have a timer of 45 minutes, and that when the timer goes, we stop and we stand up and walk away and walk around and do some stuff for between 10 and 15 minutes with a timer on. We're going to go through 35 integrals in 45 minutes. Focus. Okay, these are the 10. I promise you everything else we do comes back to these 10. Never ever think about integrating, always think about differentiating. What got differentiated? What got differentiated here was sine. Now I differentiate in my head. Derivative of sine is cos, cool. Then I have to multiply, chain rule, then I have to multiply by the half, and I don't want a half there, so I'll stick a 2 there, and that's the end. Next one, what got differentiated? Tan. Let's just check it. Derivative of tan is sec squared, but chain rule, now I need to multiply by the derivative of the inside. Notice I'm not doing chain rule with a u. If I needed to use a u with the chain rule, this would be a nightmare. But because this is GDA, but because I can do the chain rule just by thinking, and then I multiply by the derivative of, I can do it in here, which means I can integrate. So a minus sign is going to pop out that I don't want there, so I'll add that on. What got differentiated? Derivative of sec is sec tan, but I'd have to multiply by 2. I don't want the 2 there, so I'll stick a half on. What got differentiated? Now, if I differentiate cos, I get minus sine. Don't want that minus, so I'll put a minus there. Then I would have to multiply by minus 4. Oh, actually, it's okay. Don't need that minus. If I just put a quarter here. Now let's think it through. What happens if I differentiate this? If I differentiate this, I get minus a quarter sine 1 minus 4x. Then I multiply that by minus 4. The minus and the minuses cancel. The 4 cancels with the quarter, and it works. Okay. What was differentiated? What differentiates to cosec squared? Cot. Okay, let's check that. So cot goes to minus cosec squared. Notice I never integrate. I only ever differentiate. Cot goes to minus cosec squared, so there's a minus, so I might need to do that to cancel. But chain rule says I then multiply by the derivative of the 2 minus 3x, which is minus 3. So actually the minuses are okay, but I need a third. Okay, what differentiates to cosec cot? The derivative of cosec is minus cosec cot. I don't want the minus, I don't want the 7. Done. Okay, right, E, what got differentiated? E got differentiated. The derivative of e to the blah is e to the blah, but then I'd have to times by 4, chain rule. So I don't want the 4 there, so I put a quarter at the front. Next, what got differentiated? What got differentiated was 3 to the. Okay, let's think this through. Derivative of 3 to the is 3 to the ln 3. So if I differentiate, I'd have to multiply by ln 3, and I don't want a ln 3 there. So I'm going to divide by ln 3. Okay, so derivative of 3 to that is 3 to the ln 3, but that's okay, that would cancel. But Then I have to multiply by the derivative of the inside, which is a 4. The derivative of 4x plus 1 is 4. Don't want a 4. Put that there as well. Done. What got differentiated? It was 4x add 1 to the 11. How do I know? Because I know what differentiation does. It pulls the number down and takes 1 off. Okay, so let's think it through. If I differentiate 4x plus 1 to the 11 would come down and change to a 10. So I'm going to just put an 11th there for it to sort of land on. 11 comes down, lands on that, cancels, changes to a 10. Chain rule says I would now have to multiply by the derivative of the inside, which is 4. I don't want a 4 there, so I'm going to have a quarter as well. So imagine a quarter times an 11th. That's 1 over 44. Done. What was differentiated? Len was differentiated. Maybe I'd better use modular signs just to be strict. The integral of sec x is ln sec x plus tan x. Yeah, the derivative of sec is sec x plus tan x. This is what I mean. Try not to learn any integrals. Try to never ever think about integration. Integration doesn't exist. The more that you build up methods for integrating, methods for differentiating, they're just going to merge into each other and you'll always be confused. The only thing that integrating is writing down what was differentiated. So the process that you're doing is always differentiation. That's the process that you're doing. You're never ever actively integrating. That's what causes problems. You will find, like in the comments a lot, that I'm saying to students, you're trying to integrate it. Stop trying to integrate it. Look at it and think what was differentiated. It's the most helpful piece of advice I can give you in terms of this topic. Right, ln 1 minus 4x would go to 1 over 1 minus 4x. Notice I'm differentiating. I'd have to divide it by minus 4 though, because I don't want that minus 4. Done. Right, these are the only things you ever integrate. The only things. You integrate cos and sine and sec squared and cosec squared and sectan and cosec cot and e and a and 1 over x and x to a power. That's it. And the way that you integrate them is you write down what was differentiated. So the thing that was differentiated has to be one of these 10 because they're the only 10 things you can differentiate. The answer is always one of these 10. Always. There aren't any other functions. Okay. Number 8, it's exactly the same as everything else. What I did was I looked at it and I thought, what got differentiated? And well, let's look at the list. Something got differentiated, right? Something did. And it's one of them. So what could it possibly be that I differentiated to end up with this guy? Well, it can't be sine or cos or tan or cot or sec or cosec, can it? And it can't be e. Otherwise, that would be an e, and it can't be ln, and it can't be that. So it must be a to the x, 3 to the x. 3 to the 4x plus 1 must be what was differentiated. So just that process of thinking through, that's what gave me this 3 to the 4x plus 1. Now, what I'm doing, everything I'm doing from this point is differentiation, everything. So what I thought was, what is the derivative of 3 to the 4x add 1? It is 3 to the 4x add 1 ln 3 times 4. That's what the derivative is. I'm differentiating using the chain rule. This is the derivative of 3 to the. The derivative of 3 to the is 3 to the ln 3. And then I just look at it and go, what did I want? What have I got? Are they the same? Have I worked out what was differentiated? Almost. These guys are sitting at the front there, that 4 ln 3. If I differentiate that, I'd have a 4 ln 3 at the front. Don't want a 4 ln 3 at the front. So that's why I put that there. And now it works. That is the whole of integration right there in those 10. Now, I'm going to show you another 4 next that are basically these 10. But don't necessarily look like they are at the beginning. Okay. So these are the 4 that you need to keep an eye out for, because lots of people use parts here. Have a look. If you've learned integration by parts, would you think that was integration by parts? Would you think that was integration by parts? Would you think this was integration by parts? Maybe, yes. But integration by parts is not what you do when there's a product. In differentiation, we have a product rule. In integration, we don't have a product rule. It's not that integration by parts is the product rule for integration. That's not true. That's not what parts is. At the end, I'll tell you what parts is for. It's not for any of these guys. So let's have a look. What got differentiated? Now, this is where you need to do the chain rule without using a U. If you go back to the chain rule, if you write down U equals du by dx equals, and then you write down blah, 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 U equals y, and then you do dy by dx, dy by du equals, and then you write dy by dx is dy by du by dx, this is going to be almost impossible for you. Because your brain just, what you're asking your brain to do something that it's never done, which is to just see what got differentiated, to just be able to differentiate in your head and using the chain rule. And you can't do that if you've never done it. So this is why I talk so passionately about not using a U in the chain rule. It's because of these guys. So all of these are ones that you can just write down the answer. None of these require any work. The first one, what got differentiated, was sine x squared. I need a half. Done. We don't need substitution. We don't need parts. This is my whole point, that if you're taught parts and substitution too early, then you latch onto them because they're rules, they're methods, they're formulas. And it's like, well, can I use this method? Can I use this formula? And so what I do is teach integration for about 5 months, September, October, November, December, January. And then when people are really, really good at integrating, I say, right, I'll show you a couple of others for the things that we haven't been able to do yet. All right, so what are we looking for? This one here, number 11, this is an example of this 4th one, look. Trig function applied to stuff. Trig function, stuff, but the derivative of that stuff is at the front. So I can just see that the chain rule has been used. So I just know what was differentiated. Other examples, that number 12 is an example that looks like this. The derivative is on the bottom. The function is on the bottom, some stuff. Its derivative is on the top, which means it's come from learn. Exactly, Katie, well done. It's come from learn. The 13, that's an example of this one. I've got e to a load of stuff, but the derivative of the stuff is sat at the front. And then number 14 is an example of this one. I've got some stuff to the power of 2. And then I've got the derivative of the stuff sitting next to it. Now, all of these are going to be 2 marks, method, accuracy, more or less getting it right, exactly getting it right. And that you can't spend ages mucking about with parts and substitution for something that's worth 2 marks. So this is really, really important, okay? So next one, this has come from learn. The derivative of 4 minus cos 2x is 2 sine, the derivative of minus cos 2x, cos goes to minus sine, so the minus and the minus would cancel, so I'd get 2 sine 2x. I don't want the 2, so that's a half done. Okay. Yeah, the mark scheme says attempts to integrate, for example, a raised power. So method mark here would be for having sine x squared, and then the accuracy mark would be for the half. Here, the method mark would be for ln 4 minus cos 2x, and then the accuracy mark would be for the half. Okay. Ruhab, it's not that if you can't do parts or integrate or substitution, then what do you do? This is really, really important. Integration is these. That is what integration is. All that parts does is turn it into one of these. All that substitution does is turn it into one of these. All that trig does is turns it into one of these. All that fractions does is turn it into one of these. You still have to integrate. These are the only things that you integrate. Okay, So there's the basics. This was when it wasn't really difficult to work out what was differentiated. Just look down these 10. And then these are sort of level 2. This one has come from this guy. That's what was differentiated. And then chain rule minus 2x, x minus a half, done. This one has come from tan cubed. Be a third, done. Isn't question 11, what happens when you differentiate sine? Don't forget, never ever think about integration. Your thinking is always in this direction. What happens when you differentiate sine x squared? Yeah, exactly, cos, correct, that's what we want. Never ever think in that direction. No, stop. Okay. Tan cubed, I realized it was one of these. It's what I'm looking at there is tan squared, like tan like this with a 2 there, and then the derivative of tan. So because I do chain rule in my head, which you can too, you can just see, you can see that what got different. Don't forget, I'm not integrating here. I'm not integrating. I didn't do anything to get from there to there. And that's why I think you're confused, because you're looking at tan squared sec squared and thinking, what did you do to get from tan squared sec squared to a third tan cubed? I didn't do anything. That's not what I did at all. I didn't do that at all. What I did was I looked at this and I thought, using all of my knowledge of differentiation and how differentiation works and how the chain rule works, let me think. What could I differentiate and end up with tan squared sec squared? Okay. Yeah, so Katie, it's not that if the derivative is there, you can use the chain rule. It's that if the derivative is there, the chain rule has been used. What we're trying to do is work out what got differentiated. So if I come up with a function in my hand, and then I say to you, I'm going to differentiate it, but I'm not going to show you what's in my hand. And I go, da, 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 da. And then what I come up with looks like that. Then you know what I differentiated. If it comes out like that, you know what I differentiated. If it comes out like this, there's only 4 types, then you know what I differentiated. Okay. Now, this topic is very, very difficult, right? Integration is the hardest thing in the whole A-level. Leaving it to the end of the year is a really bad plan. You have to teach it way too quickly and it never ever settles because it's so huge and it's so non-algorithmic. So if you're struggling with integration, that is 100% totally normal. Even the brightest A-star students learning integration at this time of year from a book or from videos, really, really hard. This is much better done slowly from September all the way around the year, very slowly, not in 45 minutes. However, we are in the situation where we're trying to finish this, and I want to give you an idea of the type of integrals that there actually are. Okay, we've only done 14 of them. We've got 27 minutes left. So I'm going to push on, but before I push on, I want to show you and remind you the structure of what we're doing here. So what we just talked about, the 10 and then those 4, that is the whole of integration. That's it. Okay, that's it. Now we're going to look at some ways of getting to those 10 if we don't have those 10. Okay, none of these can I just write down the answer. None of them. But I can do some sneaky algebra to fiddle around with them. And then things that are not the 10 are going to become the 10. So here's what I'm going to do for the first one. X over 1 plus x is the same as 1 plus x minus 1 all over 1 plus x. Those of you who've done lessons with me will have seen this trick a lot. I really like it. I added 1 and then took it off again on the top. That is true, what I just wrote. You can't deny it. So that means I can write it as 1 plus x over 1 plus x minus 1 over 1 plus x, which is 1 minus 1 over 1 plus x. Fiddly little algebra trick. Now I can do it. Look. Now it's 1 over 10. Done. But you can't, this is the thing, what we're doing is turning not the 10 into the 10. So you have to be really good at the 10 so that when you end up there, you're like, boom, done. Has to be super duper easy. Next one. Oh, now this one I can just write down, can't I? Yes, I can, because the derivative of the bottom is on the top. So this is just learn. No fancy tricks needed there. The end. Let me just think it through. Minus, there'd be a minus 3 out x squared, and I don't, so there we go. Done. Done, done, done. Any others like that? The derivative of the bottom, no. The other one, no. Okay, bad luck. But at least there was one. Always when you've got fractions, always think, is it like this? Is there some stuff on the bottom? And then on the top is the derivative of the stuff. Because if so, I know what got differentiated. Learn. Maybe I need to fiddle around with it a little bit. But okay, have a look at this guy compared with number 15 compared with number 18. See how similar they are? Really, really similar, right? But with number 15, I needed to use this kind of, you could use division, but I just used a little sneaky trick, but you could use division. And with this one, what I can do is I can write 1 plus x all over 2x is 1 over 2x plus x over 2x, because it's that nice V shape. And then that's 1/2 x to the minus 1. Maybe I'll just leave it as a 1 over 2x actually. Add a half. Okay. So what am I doing now? Am I doing integration? No, I just did algebra there. Fiddly, fiddly algebra. Annabelle, what if you can't do it that fast or that easily? The investment in your time needs to be in algebra, in trigonometry, and in differentiation, because this is where it's needed. If you can differentiate, particularly the chain rule, if you can do algebraic fractions and partial fractions, if you know your trig identities, then this stuff is doable. And what's going to hold you back from this is trig and algebra and differentiation. These are integration. That's what integration basically is. Right, this one I can now do. So this has come from ln 2x with a half, and then that's a half x plus c, done. So the process, the algebraic fractions, or the, what did I do there? I did a little bit, this is just algebra that I'm doing here. That's just algebra. This was a bit of algebraic division or synthetic division, or just a little trick, however you want to think about it, fiddling around. This one is always remembering that some fractions you can just write down the answer. This one, this is a bit of a pain. I need to use division on this one because I've got x squared over x minus 2. Yeah, so this one I do need to do some division, but I've got my lovely division method. 1x squared, no x's and no numbers. 2 is what makes the bottom 0. Put 1 there, 2 times 1 is 2, add them up as that, 2 times 2 is 4, add them up as there, that goes there, that's 4, which means that was synthetic division you just witnessed there. It's lovely, I love it. Which means that x squared over x minus 2 is equal to x plus 2 plus 4 over x minus 2. Ta-da! Isn't that lovely? I know, this is the thing. It's all of these things are at your fingertips, but you have to know that they're in your toolbox. Otherwise, what can you do? So let me give you a summary of what I've actually done here. All the stuff that looked really magic, but actually isn't. Here, I basically did division. I'm not going to call it algebraic division. I did synthetic division. To be fair, I did it using a little trick, which I quite like, but I just did division. It's the same as I did here. This is division. It's called synthetic division. I much, much, much prefer it to anything else. This one, this is just like GCSE, isn't it? You learn this right at the beginning, that if everything is over the same thing, then, you know, like A and B all over C is A over C and B over C, GCSE algebra. This one, I was remembering the 10 and the fact that with a fraction, I always look at it and see if it's like that. Okay. Right, but so Ibrahim's saying explain the tricks. Now, what I'm doing in this session is I'm trying to show you the structure of integration. I'm trying to show you that there are only 10 things and that there exist these tricks to pull it into the 10. Now, if I do a session, I can do a session on algebraic division. I can do a session on GCSE algebra manipulating fractions. I can do, you know, all of those things. I will be doing sessions on trigs so that you know the trig identities, but at the moment, in this 45 minutes of which we have 20 left, in this time, I'm talking about integration, not division, not trigonometry identities, not the chain rule, not partial fractions, not all of those other things that come in the algebra and the trig and the differentiation feed in. Yeah, they are exactly what we need to work on, but I'm not going to get sidetracked down there in this particular session. Okay, now synthetic division, I already talked to the first years today. I've added it on to the ones you've got free for the next 24 hours. So in the next 24 hours, you click on content guide. And if you go to the one that says factor theorem and algebraic division, or factor theorem and division, I think it's called, it will be free. So you can have a look how to do what I just did. Okay, that is in there for the next 24 hours for free. So what did I achieve there? I now know that all I have to do is integrate this. And I can integrate that. That is a half x squared, add 2x, add 4 ln x minus 2 plus c done. So little tricks that turn not the 10 into the 10. Some more little tricks that turn not the 10 into the 10. Sine squared, I use the half double angle formula. You might know it's double angle or half angle, but sine squared is 1/2 1 minus cos, and then you double the angle. What I'm using there is the formula, which is a rearrangement of cos 2x is 2 cos squared x minus 1. And I've rearranged that to be cos squared x is 1/2 1 plus cos 2x. Or, you know, the other way of doing it, cos 2x is 1 minus 2 sine squared x is another way of doing it. That's the double angle formula. Rearrange that and you get sine squared x is 1/2 1 minus cos 2x. So that's all I'm doing, is just using that. Now I can integrate it. Oh, good point. Question 19 is partial fractions. Question 19, the bottom factorizes, so it's partial fractions, but I don't have time to teach you partial fractions in this time. Yeah, Rehab, I've told you right from September, I've been working with you, saying you must do integration, you must do the chain rule, it's really, really important. Trig, right? It's the double angle formula. It's this formula rearranged, and this formula rearranged allows me to change cos squared into cos. And then once I've changed it into cos, I can integrate. What about tan squared? How am I going to, nothing differentiates to tan squared, nothing. There is nothing that differentiates. You go, oh, I'll differentiate this and I'll get tan squared. No, look, no, 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 no. So at the moment, I'm kind of staring at it going, well, I don't know what got differentiated. But if you know your trig identities, you know that tan squared is sec squared minus 1. And now I know what got differentiated. Yeah, Ibrahim, you're quite right that what I've made happen is I've made it much easier to integrate, but it's actually more than that. It's more powerful than that. I've made it able to be integrated, not more easy to integrate. Literally, I've made it possible to integrate it. These are the only things we can integrate. Cos sine, sec squared, cosec squared, sec tan, cosec cot, e to the, a to the, 1 over, and x to the. That's it. That literally, that is it. So I haven't made it easier. It's like parts and substitution. They don't make the integral easier, they make the integral possible. They change you from something that isn't one of the things to something that is one of the things. That's what's happening. Cot squared. Cot squared is, do we know what cot squared is? It's cosec squared minus 1. So therefore, this will be cosec cot with a third done. No, no, Ronnie. What differentiates to make cosec squared? Let me look down my list so that I'm not being silly. What must I have differentiated? Cot. Cot is what I must have differentiated. Da, da, da. Cot. Okay, so not the 10. Use an identity, always the same identities, the 10. So every trig one squared, you should just know how to integrate. There are 6 trig functions, right? Sec squared, you know it was tan that got differentiated. Cosec squared, you know it was cot that got differentiated. Sine squared, you need to use this double half angle formula and then you can do it. Cos squared, same formula, well, sort of same formula, and then you can do it. Tan squared, use the Pythagorean identity. Cot squared, use the Pythagorean identity. Good point, Katie. It would be minus. Absolutely agree. If you differentiate cot, you get minus cosec squared. If you differentiate cot, you get minus cosec squared. I didn't compensate for that. I need to put a minus on. Very, very good spot. Right. Substitution. Now, do you recognize these 4? These 4 are the ones where I just wrote the answer down. Do you remember? Yeah, I just wrote it down. These are the 4 where I just, these are the 10, but like level 2, the 10. And I just wrote the answers down. I just wrote them down. But these are the situations where you might have been shown substitution. It's massively overcomplicated, but it works for that's what substitution does. So I'm just going to show you how it works. I choose, first of all, I'm just going to put by du there. I always start with that. I'm going to put my u equal to x squared. So du by dx is 2x. Right, now I'm going to rewrite it. So I've got an x, and then I've got cos u, and then I've got dx by du. That cancels with that, leaving me with 1/2 cos u du. The derivative, or the thing that differentiates, must have been sine. And now I finally go back and I replace the u with an x squared. Okay, JLo, this is the where we're coming to. So when do we use substitution? When do we use parse? Can you see that the substitution that I used worked here, but it wasn't necessary? Because I already knew just by looking at it that the answer was 1/2 sine x squared, because I just looked at it. And I can see that the derivative of the x squared is there. So I know what the person differentiated. I know they differentiated sine x squared. Same thing here. What I'm going to do is I'm going to have a substitution. I'll just put my by du. I always start like that. U du by dx. There. So sub it all in. I've got sine 2x on the top. Got u on the bottom. Dx by du is 1/2 sine 2x du. That cancels that. 1/2u du, which is ln 2u with 1/2. And then I'm going to put that back. Oh my goodness, it's so long. Blah, 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 blah. Yeah. So sure, you can use substitution on these ones. And you should have been taught that. If you haven't been taught substitution yet, then this will be a bit like, whoa, what are you doing? But it's a method that you just go through the steps. You identify the U. Oh, Raseb, you're saying that you prefer the substitution. I don't know why. I know why, because it's got steps to it. We like things where there are steps to follow. That's why we like substitution and we like parts. The whole rest of the integration is like, well, how are you doing? What are you doing? Like people said to me with this one, all the way back here. Do you remember? How did you get from there to there? What did you do? What method did you use? What steps did you follow? How do you know? What did you do? What were you thinking? I was thinking, I wonder what got differentiated. So all of this stuff here, all of these 10, people hate. But that's what it is. That's what the whole of integration is. We can use techniques of fractions and algebra, maybe even binomial expansion we might use. We might do a binomial expansion here to get a approximation. And then we could use that, or we could use small angle approximations with trig to get something that we can integrate, but we only ever integrate the 10. Okay, let's have a look at parts and substitution and when we would actually bother using them. So all of these ones, I'll let you have a play, but if you put u equals tan x, it will drop out, but you'll get the same answer that I was able to get with nothing. And you will be able to get with nothing if you go away and practice your differentiation. It's by practicing the chain rule that you suddenly become able to integrate. Now, these are ones where actually substitution is properly useful, properly useful. So using u is 2 minus 3x, or u is 4 minus x square rooted, or u is 3/4 sine theta, properly actually useful. Okay, I can't look at these ones and see what got differentiated. Okay. The main tip that I have for you about spotting what is u is that you spend ages and ages doing the chain rule and the 10. So that these ones need to stand out. These ones need to be like, whoa, I don't know what got differentiated. Because you need to be so used to the ones that you can see what got differentiated and all of the little tricks and fractions and algebra and trig and stuff to get you into the things that can be integrated, as in you know what was differentiated, that these ones are like, what? Because we don't know. I'm looking at it and I'm going, I don't know what you differentiated actually. It's really hard. And that's where substitution is useful. So let's go through the method and then we'll finish off with parts. Start with by du. Write down what u is and differentiate it. Sub in to the integral. I've got an x and I've got u to the 11 and then dx by du, which is minus 3. Extra little job. I don't need that u there. That's an extra job. That x, that's a pain. So I need to go back to my substitution and rearrange it. And now I can sub that in. And then finally, that 3 cancels that. I've got u to the 11, u minus 2 du. Which is, if you expand it, u to the 12 minus 2 u to the 11 du, which I think you can do, and I think you can do it in the first year. Oh, it is a third, you're right, dx by du, it should be upside down. So this is actually like that, which means it is like that. So they don't cancel, they produce a 9th, and that 9th sits at the front. You're completely right. Minus a 9th sits at the front. Whoop, whoop. Yep. Okay. Now don't forget, I've made all these free for the next 24 hours. Proper lessons where I go through properly what's happening. What I wanted for this 45 minutes was the overview. the idea of how it all fits together and what's important and what the techniques are and why you use the things you use and when you don't use them. 31, u is 4 minus x to the half. So oops, I didn't do by du. So du by dx is chain rule, like that. Now I'm going to sub in. I've got 3x on the top. On the bottom, I have got u. Then I have got 1 over 4 minus x square rooted. That's just u. And I've got a minus a half as well. Let's just tidy this up a bit. 3x over u squared. There we go. Extra job. Extra job. Abraham. Good one. Extra job. The x. So same as this one, same as the first one, really, really common, same structure. Go back to the x. Go back. U squared is 4 minus x. So x must be 4 minus u squared. So actually what I'm looking at here is 3 lots of 4 minus u squared all over 2u squared du. Now, I've done all of the work. Has it turned it into the 10? Yeah, it has. This looks disgusting, but this is equal to just fractions, just normal GCSE fractions. This is equal to minus 12 divided by 2. So minus 6 u to the minus 2 plus a half du. Can you use, yeah, exactly. This is exactly the same as u squared is 4 minus x. It's the exact same, yeah. Okay, last one. These are ones that are funny because they're like the other way round. It's not what you would imagine. Oh, I need an x in there. That should be an x, not a u. There we go. So these are a bit weird. Rather than having u equals, you set x equals. And these are the ones I'm pretty sure that they will give you in the exam. They will tell you the substitution. Shouldn't it be 3 over 2, not a half? I'm not sure where you mean, and I'm aware we've only got 4 minutes. So I am perfectly willing to believe that I've made a mistake. If I have, I would put it in my FFS journal. But I don't know, like, I wouldn't worry too much about, I utterly believe I may have made a mistake somewhere there with numbers. Okay, how do we do this? We do exactly the same. We go by du, and then we differentiate. And then we sub in. And then we put the dx by du there. Oh, it's the right way up. I don't need to do that. Dx by du. And this has got a square root over it. Little bit of fiddling around. Little bit of fiddling around is going to get me that. 1 minus sine squared is cos squared. So this is that cancels that cancels that, and the whole thing reduces to this. So the detail is a pain. The detail and the algebra is fiddly, definitely. Fiddle, annoying, difficult, lots of mistakes, lots of FFS journal coming in here. But the structure of the substitution is always the same. Wouldn't it be cos squared on the bottom? No, because dx is sine theta. So dx by d theta is cos theta. And I was subbing in dx by, oh, it's d theta. Dx by d theta is what I was subbing in. So that's dx by d theta. Okay. Yeah, it is. It is not easy. It's the hardest thing. Right, let's see if I can tell you when you need parts. There are only 3 situations when you need parts. Only 3. Ruhab, in the last question, it wasn't u equals. It was x equals. Right, parts. Okay, parts. You are looking at this and it is making you sad, because you can't integrate it. It's not the 10. U dv, not the 10, therefore can't be done. Only the 10 can be integrated. Sad? No. But look, if we have a different combo, if we have this combo, v and d, that should say du, v and du, this is great. We can do this. That's what parts is for. And there are only 3 situations where that happens. Situation 1, you have x stuff or x squared times e to the x stuff. So, like this, x stuff, e to the x stuff. Situation 2, x stuff could be x squared, but it's a bit of a pain, times, break the rules of action hours by 30 seconds. So e to the x stuff times x stuff. Trig x stuff times x stuff. So by trig, it could be sine, something you can integrate. Sine, cos, sec squared, cosec squared. Well, you probably wouldn't have sec tan and cosec cot, but you could. Or anything to do with ln. Anything at all to do with ln, we need parts. Anything that is of the structure, stuff to do with x times e to the x, or stuff to do with x times trig. They're the only 3 situations for parts, the only 3. First one, we put u is x, and then we differentiate it. We put v prime is e to the x, and then we integrate it. The formula is boom, boom. The integral of uv minus integral v du. uv minus integral v du. We end up integrating these. So the answer, well, not the answer, the way that we get it into the 10 is uv minus the integral of v du. And now we can do it. Same here. Put your u equal to your xy bits and differentiate. Put your v prime equal to your triggy bits and integrate, which means work out what got differentiated. This is the formula, uv minus integral v du. The answer is uv minus integral v du. You don't use parts when it's not the 10. You use parts in situation 1, situation 2, or situation 3. That's when you use parts. Situation 3, ln. You use u is the ln, always. And you use v is anything else. In this case, there's nothing else, so I'll put a 1. If there was something else there, I'd put the something else there. Integrate it. uv minus integral v du. uv minus integral v du. The end. Slightly over. So let me do a summary for you here. This is number 1 summary. This is a very, very difficult topic, and there is a lot in answer to Kate's question. How much integration and differentiation is there in the exam? Probably about 20% of the marks are for integration and differentiation. I'm going to add it to your course map on average how many marks there are for each of these topics. But yeah, differentiation and integration is huge, 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 huge. About 20% of all of the marks in the whole paper, okay? The summary that I want to give you is that you can't integrate unless you know your trig identities, you can do algebra, and you can do the chain rule. So don't even try, because you'll just get yourself into a messy tangle and feel sad. So go back to the chain rule, go back to the integration, go back to the partial fractions and algebraic fractions, the binomial expansion, all that stuff, and shore up those ones before you come to the integration. The playlist is 29, 30, 31, 32, and I've also added on the synthetic division, which is called factor theorem and algebra, factor theorem and division, and it's in the AS section, but you'll be able to find it. The summary of everything that we've done is that there are only actually 10 things that we ever integrate, that what parts does for one of 3 situations only is bring it back to what we can actually integrate. What substitution does is to bring it back to what we can integrate. What trig does is to bring it back to what we can integrate. What partial fractions does is to bring it back. There are 2, yeah, JLo, that is situation 1 of why you use parts, absolutely. Okay, so there are 2 things I have not done with you integration wise, which is these guys, sine to a power, cos to a power, different powers, and these guys, sine of an angle, cos of an angle, different angle. We'll come back to those. Okay, you will probably need to go through all this again. I talked fast, I did a huge amount. I tried to do the whole of integration in 45 minutes. I will come back to all of the other stuff. I'm doing an action hour at 4, okay, a study with me. Now at 4 o'clock, if you want to join in, you could be going through this exact thing and asking me questions about it so that you can go through at a slower pace, that's fine. You could put some questions up in the course, that's fine. So if you want to do more of this, come back at 4, and with my help, then come back at 4, and for the study with me, you can go back over this whole thing, okay? I hope that was helpful, even though it was quite intense. I will see you either at 4 o'clock or I'll see you tomorrow. Hope you have a good day. Yeah, fast but exhilarating. There we go. I'll see you at 4.